Our technician has to walk back. Thank you. First of all, thank you, Lada and REHVA for hosting me here. Thanks also, it was really nice to see also the previous presenters, so I'm happy to present here with my talk on From Connected to Automated Buildings. Yeah, and there's a couple of things that I would like to talk about. So I'm going to talk about my background from our research groups in the Information Systems Group in the Technical University of Eindhoven, where we have several projects which go into the topic of smart buildings, although we start from it more from an information systems point of view. So there's a couple of topics I would like to go through, which is buildings and semantics, and then moving our building data on the web. This connects a bit to the previous speakers where we want to have more connected buildings and have more data that we can use for optimizing the use of our building. And the third part is to talk about the movement from smart buildings to connected buildings. And in the end, every building is a data hub. So what I will talk about is, I will start with this building. This is a project that we're doing in our faculty. This is the Atlas building. This is a building on our campus which we use as a test environment. And this is also a project that we use in combination with the project Brains for Buildings, which is a project run in the Netherlands together with TU Delft and TNO and a number of companies. What we want to do in this building is that we want to make this building smarter. We want to make many buildings way smarter and make sure that control is done appropriately using similar mechanisms that we have seen before, including machine learning and so forth. And to do so, when we do this, we want to actually model the systems that we have in our building. This was briefly already presented by Heikki, where we have this flow system ontology to represent our building. We want to represent the systems in our building so we can better control them using the data streams that come in from the sensors. And something that I, as a building model, then typically encounters, we have a couple of questions. I typically say we should have our 3D model included and so forth so we can see the building. And then the question I get is why? Why do we need to have this 3D? We have our data, it is fine. Yeah, okay, so that's one point. And then on another occasion, I can then hear we have all these sensors, but we don't know where they are, what they are measuring. We would like to know more about them. So for me, those two should be matched a bit better so we have decent information available about our devices and about our buildings that we can use to make better control. And in this particular building in Atlas, I think on the left you can see the BIM model of the systems in the basement of the building. This is a 3D building model. On the right side, you can see the system in the basement where you see these stickers with the indicators, the IDs of the particular endpoints of that system. And then there's a third system, which is not on the slides, which is the building management system. And what we need to have is to have these identifiers appear physically, but also in the BMS system and also in the BIM model so we can integrate our data sets. It works typically well to have those IDs in the virtual in BMS plus the physical devices, but they're often missing in the BIM model, and then we lose a lot of potential information. Okay, so this is an example of what, for everybody who does not know what a building information model is. So this is the BIM model, a draft BIM model of the same building, floor 8 and 9, I believe. And what we are doing there is that we, in the BIM environment, you model every single object separately. So for every wall and every door and every column and every piece of glass, every sensor, every piece of equipment, we have a 3D object with a whole bunch of information available. And so all those objects have properties, which you can see on the left side. One of the most basic things to do is to make sure that your identifier appears on the left side, and you can make a connection with the BMS system, which will be deployed in the building. So this is our context. That's also what we go through with our students. So we have on the top left side, we have building information modeling, which includes digital twinning. So we have the real environment and we have the virtual environment, which we need to connect to make sure that everything is matching. We have our building management system. And here in a very small image, you can see the 2D floor plan of the building, which is best available at this point. And then we have this overall way of engineering a building. For example, here on the right, you can see how a new building is being engineered to be constructed. So we have an architectural model available. We have a MEP model available. Both discipline models or aspect models are combined in a coordinated model. This is delivered to the facility management office, and they have that building available. This thing needs to be connected then by real estate department to the BMS environment, so we know which is which. If that happens, you have a better amount of information, and you can improve the optimization of your building, basically. And that's kind of the background where I come from. So I will go step further into this. So if you want to know more about this buildings and semantics, there's a book that I co-edited with Chris, which talks in 11 chapters. It's only this thick, so it's actually doable to read it, which is about data modeling, how to model the different kinds of data in our building and how to use it then in your environment. Things that some basic principles that we then, based on all of this, we have some basic principles that we rely on typically, and that is we want to integrate the data. And I will add here that that is also not a problem. We actually can integrate data. Our technology is quite well advanced these days. There's lots of technologies available. And from my point, so from our project perspective or research perspective, this includes, for example, the BIM data, building metadata, so the description of the building. But also, so that's the more static data. It doesn't change every day. Your building doesn't, the wall stays there. But we also have this more dynamic data, telemetric data, and sensor data that we want to combine with these metadata. We have perfectly capable web technologies. We have actually pretty good communication protocols by now, and that I think is a very reliable basis to go forward. So I don't think that's really a problem. And this needs to be shared via user-friendly and user-centric interfaces. We saw a couple of them already. I think it should be even more user-centric so that we as a user can go into a building and can get a certain level of access to how the building is operating. So this is kind of the background of where we are in trying to build systems for building management. How do we get this on the World Wide Web? There's in the construction sector, so this is a different sector where we actually construct building, there is a movement to transfer the modeling exercises from AutoCAD and so forth into a more web-friendly environment. So back in the days, so a decade ago, these were technologies which are bespoke, where you have to download software, model, and then you have a file. You have to print the file and send the file to somebody else. In this construction sector, they use this schema called IFC, which stands for Industry Foundation Classes, the foundational classes of the construction industry, so wall, column, and so forth. And they want to move this schema more to a web-friendly environment, which includes XML, that's already a bit older, but also JSON, lots of APIs, and then we have this linked data, which is RDF. So they want to make our building data more usable on the web anyway, which I think is a very good idea. And this is then a schematic. I will not go into much detail here about this schema used for building information models. So whenever a large construction company builds a facility like this and they make a BIM model, they will basically typically rely on an IFC schema, which is a class diagram schema that says a wall should have a height and a length and a width, and there should be a door in it, and there's a window, and the window can have certain properties. So this is the schema of this 3D building model, and this is available typically in an express schema, and this is the data that's then the actual building model that you transfer from one person to the other. So that's the pictures that you saw before and the videos. And they are looking now into alternative representation mechanism, which is XSD and OWL, and these are then the data formats. I will not go into much detail here. The idea is then these two are now standardized. They are not standardizing the lower one, and for that lower one, we're taking a slightly different approach. So the building smart industry is basically working on this XML and Express files, which display the building model. On our end, we are basically trying to make link building data graphs, which is connecting the different data sets about our building. You have seen some of it. I will not go into full detail here, but you have seen some examples already. For example, the FSO, HVAC that was a diagram that was such a link building data graph. So these are graphs with specialized vocabulary, such as brick, such as bot, such as an MEP vocabulary, real estate core. These are larger vocabularies, and they allow you to describe a building for a particular part. For example, SSN allows you to define all semantic streams as a network. Brick is specialized in describing the individual points in HVAC systems, any system. Bot is building topology. MEP describes all of the mechanical equipment and plumbing devices. So we have basically a network of information. These two are not incompatible, they are compatible. So you can transfer this data to here and actually work with this semantic data. This is what it then looks like. So this is a graph. So it's the lower part of this graph that describes an individual building. This is our Atlas building on our campus. So we see that we have a building. This is the building. It has a number of stories, story 1, story 2, story 113. And this story has a space. The space has a number of interfaces to elements. And it also has adjacent windows and walls. And this keeps being connected. This is a very flexible mechanism. As you can imagine, you can just drag more arrows and nodes. And you can easily connect this to the devices in the building, so the HVAC devices, for example. And this is then used by Granlund, for example, to describe the flow in the flow system. So the flow through the HVAC equipment. It is not only a graph, it is also a graph that follows a certain vocabulary. So it's a well-defined vocabulary, which can be standardized among a group of people. That's what Brick is doing. Brick, they basically make one schema for that particular industry, which they then all support. And if we apply this to our nice little building here, here on the right, we can see this is the eventual graph. This is a part of it. I will not fully explain it, but it shows you two sensors. So there's this PIRs, so the peer sensors, occupancy sensors, infrared. There's another occupancy sensor here. You have some of the semantics explaining the metadata of these sensors. And these can be combined to spaces which are connected to the BIM model, and that gives you then more information. So we can link our space here with our graph and find more data. Wow, okay, nice. So this is the background. So we have all of these graphs. Pieter says we need to have more graphs. And I try to, there's a difference in kinds of graphs. Some of them are more complicated than others. And I try to put them on a scale. And the scale goes from green to blue, so not red to green, which means nothing is really bad. It's just all fine. There's just a spectrum of schemas that you can use to describe your systems. And I'll explain you this. So on the left, you can see a more normal tagging and metadata approach, which is where you can find those labeling approaches, plain labels, and Haystack is tagging your devices. And you can use those tags to find the equipment that you need. On the far right, you have more symbolic AI, which is semantics, and you have a fully defined IFC schema in full detail, which is very restricting. So you have to follow the schema or you're out. The left is way more flexible. So many people in practice are typically here because it's so flexible. We would like to move a little bit more to the right and end up here where we have brick, link building data, SAREF, and real estate core that allows us to have a bit more semantics than what we currently have in our most smart buildings. That being said, so what we typically do, we typically rely on these vocabularies. So these are specified vocabularies that allow us to describe this system. And then it allows us to query this building system to say, what is this thing here? Can you give me some more information? Yes. And then you can get a certain identifier here on the left, which you can then use to do more operations. Building data on the web, that's where we are. So we have these graphs and we can manage it using our vocabularies. How do you now move to these connected buildings? One of the takeaways that you could go home with is to say, well, there was this person on stage, he said we should convert everything to graphs. No, stop. So we should not transform everything into graphs. Not everything can be a graph. So we have plenty more data that is very difficult to put in a graph. For example, we have 3D geometry. The geometry itself is very difficult in a graph. We have time series data. This is not a particularly great picture, but we have time series data that is also not easy to put in a graph. They come in as IoT data streams, and they should remain such. We have 2D data here below. We have geospatial data. This is also GIS data. We have meshes. So we have all sorts of data. We don't have only these graphs, but the graphs do help us. So which data sources do we then normally get? Well, we have, this is too much text, don't start reading it, but if you look at the green, so we have our semantic data models, which are the graphs. They define the semantics of our system, and we have a whole range of semantics of schemas already available, which is super helpful. And there's a rather modular approach here to organize it. So we don't have one schema for everything. We have specialized schemas, and you can use multiple together. Second, we have more time series data, which are supposed to happen in time series databases, and then you can apply the machine learning algorithms that we already apply appropriately, and that needs to go in a separate database. And then we have specialized formats such as images, point clouds, documents, 2D and 3D data, which are blobs of data that you want to load as fast as possible, typically. So we have different types of data, which means that we need to have an approach that allows us to access these different types of data simultaneously or as preferred. So we have on the one hand the geometry here, we have our semantics, and on the other hand, the third part is these IoT data streams. They are different kinds. And what we are looking into is to make those available in one platform, which we do, well, it's digital twinning, and it's also having a server. I think that's kind of obvious, but so we try to make this available also as a server to access these streams. And we take care that we have dedicated, so fitting information systems, so fitting storage, and it's well organized and accessible from that server so that you have fast enough access. And this is then what you would call a system architecture. I try to motivate one of our PhDs, Lasita here. She is one of our PhDs, and I say we need a reference architecture. We need to have an architecture that says this is how we should integrate all these data sets, and that is available here on the left in this article, which is an end-to-end implementation of a service-oriented architecture for data-driven smart buildings. So you have the semantics, but you also have the data, so you can actually do all of the things that we have seen in the previous three talks as well. And that is going really well. So we have this reference architecture. This is the architecture. I can't explain this obviously here in detail. None of this is specific software. So many of these, if you fill this in with specific software, you will end up with what people are currently trying to build anyhow in many companies, which I think is a good direction. And there's a couple of things that I could say about it. So we did one test here. At the moment, what we are experiencing in the project is that the buildings that we encounter, they don't have their data so well organized, let's say. So it's difficult to find the data. So we end up typically with custom naming schemas. This is one of them. So we have this naming schema which says building 33 has an air handling unit with a certain valve, and there's a control command here. So this is the kind of data that we get in an Excel spreadsheet, or it's used in the BMS system in any case. We made a Python transformer which makes it possible to have a graph of the system available. We keep the IoT data streams. These are then transferred via MQTT, and the graph is connectable via HTTP. And on the right, you can see a Grafana dashboard which connects to both of them. So you first find the space and sensor that you want to have. Second, you get the stream, and then you can do data handling, basically. Yeah, one of the challenges that we have here is that we have many of those custom naming schemas, and it would be nice to standardize a bit more. But yeah, that's something we try to do with the companies. A second example that we are working on is this project together with Bosch. It's here on the bottom right. So the German Bosch company. We want to basically use so here you can see another diagram which is similar to what I said before. We have a graph database. it loads the BIM data in it, and then we have the time series database, which connects to sensors and actuators. There's an integration layer, which you can imagine as being an API-based system, service-oriented, that allows you to connect to forecasts and controls for the pricing, for example, and then to have a message back to change the system. So we try to, with Lou, another PG, we try to do semantic-assisted model predictive control as good as we can. And this is then an example of the interface. This is not live, it's a video, obviously. So we are able to go into our building to select the equipment that we would like to have. You can see that Lasita selects the space. We are now space-oriented in this particular case, not device-oriented. So first you query the elements, then you query the data stream, and then you can inspect the data of that particular location. It's actually it's not super spectacular, but it's actually very useful to have such an environment. Okay. We're trying to now apply this to the rest of our campus. And this is really nice. So all of the buildings that we have, we try to make BIM models available, and then we try to make them available as graphs. And with the data management team, we try to connect the IoT data stream so we can operate it better. Right, last point. I try to, so we're done, right? We're finished. Why is there a fourth point? Every building has a data hub. I do want to talk about this. This is the more complicated part. So I think what I shared above, I think we have lots of possibilities to actually have really smart buildings and good control. Much more than 5 to 10 years available. So we can do really a lot. So why do we have here a fourth item? Because at the moment what we do is we make, for every building, we make the data set available. And then you have the data set of our faculty, of our university, but you also have the data set of the cadastre, of the national cadastre. You have the governmental database, you have sensor data, you have people data, you have smartphones. So you end up with some kind of what is called a data mesh, with a combination of a whole range of databases. So it's not just your database, there's a whole range of databases. And these are then managed over a large period of time. So if you look at the national scale, for example, it becomes really, everything is building specific. And I think we should take care that we don't get lost in large amounts of national databases, for example. We should be able to manage our own building database and have that available and make sure that we can handle the data that we have about this building. So so there's a couple of challenges that I see in any case. So if you look at the larger area, we have different databases in different locations. We have a location of Eindhoven municipality, of our building, of the government. So we need to connect all of those, which becomes an effort. And we have a difficulty of connecting to those databases because they have different schemas, different protocols, and they also often have overlapping content. So it is possible. It's also not super easy. And also important, those external databases, they are owned by typically external parties. So we have here a data ownership challenge. And it's not only an ownership challenge, it's also a challenge of having data that might be outdated, which is not what we want to have. So we want to have up-to-date data from the people who own that data so we can make a reliable prediction. For example, if the weather predictions are wrong, then we have an issue. If a wall is in a certain location where it is not appearing, then we also have a problem. So we want to have more live data, basically. And we want to also take part as individual building owners in this larger schema. So we want to take part with our building in a national environment, but we don't want to give our data all to the government, obviously, because it's our data, we are working with this. So I think this is a pretty complicated step to take. And the future which I was thinking to have is that we would have multiple buildings, building 1, 2, 3, as nodes available that we can query. So I would imagine that if you go to a building that you want to go and log into the building, see the data that you have access to, and actually work with this kind of data. That's now not possible. I mean, you can go to the building and there will be no data. You cannot connect to anything, although there is a BMS available. You can do it for your own house, though. So I think we should try to move this a bit further, and that's where we try to go, step by step. I have very complicated slides. I am sorry. So what we're trying to do with a number of projects, for example, at Upscale, is we try to move, but we're not doing central data management, but we're trying to move from more decentral hubs to more peer-to-peer networking. We want to make the data even smaller and granular, so you can own your piece of data. So we clearly don't want to do central management, but what we now see is we have decentral hubs of data. The university has some data, the contractor has some data, the government has some data, and we can access to it. I know I have no data of my own house, so there you kind of have clusterings of data, of information. And it would be nice if every one of our buildings has actually their own data and their own, or even on an element level or space level, should be able to access our data. This is not only important for smart buildings, but also for circular buildings. If you want to exchange materials from one building to the next, then we need to have, then the ownership changes of that specific element and the maintenance also changes. Yeah, okay. So for example, if you look at this building here, I try to make an example. So you can subdivide all of its components. And what I think we should have is that every one of those elements should have an identifier, a URI, so a web-ready identifier, which connects it to the owner of that object and also tracks the information of that object. And if, for example, if a certain company, a production company that produces one of those slabs is responsible for taking that slab also back, or taking steel back, or taking a certain element back, then they stay owners and they need to know where their materials are. So they need to have access to that URI. So they need to supply the data of that element. And I think that's the same for HVAC components. So I think we should have a more of an element-oriented network of data where we can access on a almost by element level the information about that element. Okay, and that's something that we try to do with this upscale project. This is an example project to give you an impression. And I know it's not systems, for example, but it connects to it. So this is a building in Amsterdam, a circular building. And it's been rebuilt in such a way that you can completely demount it. So you can detach everything. And it's now very popular anyway to do this. And then it allows you to, for example, reuse some of these plates in another location. And you know what? They're going to do it as well. So they have just built it. They will tear it down and they will then distribute it and place it elsewhere again. So you can actually trace where those components are traveling through its entire supply chain. This is, in this case, for circular use, but many of the take-back modules or systems work like this so that you can trace where are my devices, can I take them back, what's the status, and can I improve the performance of these devices. This is another example here with a project with the MEU, where the MEU is in charge of those containers and they need to take them back. So they need to be in charge of what of how those containers are performing. So they are the data owners. I have 2 more slides, then I'm finished. And this goes quite far. So we have smart buildings, we have circular reuse. If you think of this, then you can imagine that every one of those elements has an ID, and you can trace the information from that identifier, from that element, which means that this element becomes a smart component that can also send out messages, maybe, who knows. And this is something that we try to do in a seemingly disconnected case. This is a small robot here, you can see here as well. And we try to do indoor navigation with those robots based on the information that we have from the same digital twin system. So we, again, connect to this Atlas building and see where the robot queries, where am I? And then based on where am I, so it localizes, it then travels through a certain route. For example, this robot basically queries, I need to go from here to here. Can I go to this location? No, yes, because I'm small enough. Here I'm higher, so I need to have a different route. And this is done by querying that digital twin to navigate your route. And this is an example. This is the same. I hope that somebody can click that button in the background. Yeah, okay, great. So this is a small video of that robot. It's a different robot. So on the left, you can see the building that we have is being transferred into our database, which is our digital twin baseline. So it says PostGIS SQL, but it can also be an RDF store. And then the BIM model is here visible in the red wall columns. Basically, they have object features, which are polylines and points, which eventually connect to the LiDAR of that robot. So the LiDAR recognizes certain points, and then it knows, oh, this point is connected to this corner, which is part of that wall and window. And you can do this only if you have the information of all those individual elements. If you don't have it, then you cannot query. So this is this rather clunky and big robot. The LiDAR is here. It sends out a two-dimensional LiDAR. It connects, bounces off the surroundings. So here on the right, you can see in the green dots, it's a bit small. You can see the points being recognized and compared with the elements that are in the digital twin. And then based on this, it can recognize I'm here and I can do this action or I can do that action, for example. This is a basic navigation test. It's a starting point in any case, but the main point I want to make here is that if we do this properly, all our BIM modeling, our semantics, as well as our equipment, our smart buildings, our IoT streams, plus a bit of robotics, then I think we can actually have more of an automated workflow and we actually have rather promising technology. Okay. This is a summary slide, and I should not forget that I also have a conclusion slide. So the conclusion slide, what I want to give away to you is that we have actually quite easy and very useful to represent. It's not so complicated to represent our information, our BIM model into those graphs. I think that's a baseline. People think it's very complicated. I think we are doing pretty fine by now. Second, don't fall in the trap, oh, I can do graphs, I will do graphs everywhere. So just do graphs where you need it and rely also on the other solutions to store geometry, which is file-based more, and also those sensor data streams, which is more data streams which connect to machine learning algorithms. And then the last point that I want to make is that I think we should transfer step by step into a more granular data storage and a data follows object proposition or ID. Thank you very much for your attention.